Hello there and welcome to chapter 12. In these first two sections, 12.1 and 12.2, we're going to begin our discussion of vectors. And so to start, let's go ahead and define what a vector is. You see here that a vector is a quantity with both magnitude and direction. Okay, so we typically represent a vector using an arrow. Okay, and the direction of the arrow, that's the direction of the vector. And notation-wise, okay, you see I'm using the letter V to denote this particular vector, and then I have this arrow over the V, and that's just telling you that this is a vector quantity. Okay, now the point from which the vector originates, that's what we call the tail of the vector, and then the point where we terminate, that's the tip of the vector. Okay, now the length of this arrow, that's the magnitude of the vector. Okay, and we use this double bar notation to indicate the magnitude, and as we'll see, this behaves in a very similar fashion to the absolute value. Okay, so there's the magnitude. Now, an important convention when working with vectors is as follows. Okay, so we say that two vectors v and w are equal if they have the same magnitude and direction. Their tails, and so in turn their tips, may be located at different points. Okay, so this is essentially saying that it's the magnitude and the direction that really define the vector, not the points where our tail and our tip are located. Okay, so these two arrows here, V and W, okay, well, their tails and their tips are located in different points. However, these two arrows point in the same direction, and the length of these two arrows are the same, and so by this convention, V is equal to W. Okay, so we always have to keep that in mind, and we'll see this come up quite a bit moving forward. All right, now I'm going to contrast vectors that have both magnitude and direction to what we'll call scalars. Okay, now a scalar is a quantity with magnitude only. Okay, so here are some examples of common scalars and common vectors. So speed, well, this is telling you how fast you're moving, but it doesn't indicate the direction in which you're moving. Whereas, so this is speed is a scalar quantity, whereas velocity, right, this is telling you how fast you're moving and it's indicating the direction in which you're moving. So velocity is a vector quantity. Okay, length, area, volume, well, there's no direction associated to those, right? And likewise, magnitude, right? No direction specified by just magnitude alone. So those are all scalar quantities. Acceleration, that's a vector quantity, okay? And acceleration, that's the rate of change of velocity. Since velocity has a direction associated to it, its rate of change will also have a direction associated to it. So acceleration is a vector. Okay, mass and density, pressure, temperature, work, and power, okay, these are all scalar quantities, right? No indicated direction. Whereas other things like force, momentum, position, displacement, so on and so forth, all have directions associated to them. So these are all vector quantities. All right, cool. So now let's talk about combining vectors. And we'll start with adding two vectors together. Okay, and this is what's referred to as vector addition. So let's say I have two vectors, v and w. Okay, and I want to add them together. Okay, so the convention here is that we're going to take, to form v plus w, the tail of the vector w, and attach it to the tip of the vector v, as you see here. And remember, since this vector here in red and this vector here in red have the same direction and magnitude, moving them in this way doesn't change the vector. So this is w and this is w as well. Okay, so it's fine to do that. Now to form the sum of the two vectors, I'm going to form this vector in blue that runs from the tail of v to the tip of w. Okay, now notice I could also form the vector w plus v in much the same way. Now I'm going to take the tail of v and attach it to the tip of w. So I'm going to follow w and then v, and notice, right, the vector that runs from the tail of w to the tip of v is exactly the same as what we got for v plus w. Okay, and given that this that v and w here, right, by moving them around in a parallel fashion, form a parallelogram, this is referred to as the parallelogram rule. Okay, v plus w So follow v, then w, and form this blue resultant vector. That's the same as forming w plus v. So follow w, then v, get that same resultant vector. Okay, so in the language of algebra, this says that the addition of vectors is commutative. Okay, cool. Now, we oftentimes, especially in physics and in engineering, will use this term resultant vector. So when you sum two vectors together, the sum v plus w, we call that the resultant vectors of v and w. Okay, so how about vector subtraction? Well, for that, the idea here, at least to begin, is to think about adding v to negative w. So what's the opposite of w? Well, we'll define the opposite of a vector to be the vector that has the same magnitude as the given vector, but it just has the opposite direction. Okay, so if this is w, negative w is this vector in blue, right? It has the same length as w, but just points in the direction opposite to w. Okay, and so now to subtract these two vectors v and w, what I'm going to do is add negative w to v using the convention up here. Okay, so let's go ahead and do that. So to add negative w to v, right, I'm going to attach the tail of negative w to the tip of v, as you see right here in blue, and then the resultant vector that's going to run from the tail of v to the tip of negative w, and you get this vector here in orange, right? So v minus w here is the same as v plus the opposite of w. Okay, now also note we could form that difference as follows. Okay, so instead of considering minus w, okay, just attach the tails of v and w, and then this vector that runs from the tip of w to the tip of v, I claim is also v minus w, right? In other words, it's just that same orange vector that we got down here. And why is that? Well, if I follow w in red, and then this vector that it runs from the tip of w to the tip of v, okay, what is that? Well, w plus what vector will result in the vector v? Well, it's got to be v minus w, right? If I add red to orange, notice the w's are going to cancel out, leaving me with just v as the resultant. Okay, so to summarize both of these, right, the vector sum and the difference, if I have two vectors v and w, right, and I attach their tails here to form the sum, as we saw up here, right, that's where I can move w, right, so its tail coincides with the tip of v, and then there's your sum vector v plus w. For the difference, just attach the tips. So if I'm doing v minus w, notice the difference vector points towards v. It points towards this first vector in the difference. Okay, very good. So now let's go ahead with all that in place. Let's talk about scalar multiplication. Okay. So for scalar multiplication, the idea here is, well, just to scale the magnitude, but we're not going to change the direction. So if I have a vector v and I say multiply v by the scalar 2, all that's going to do is stretch v out so it has now double its original length. Now notice here, for 2v, you can think about that as just taking the vector v and adding it to itself, right? 2v is just v plus v. And using this convention up above, right, if I add v to itself, I'm just attaching the tail of v to, well, the tip of v, and then forming that resultant vector, and there's 2v. Okay, now what about something like minus 3/2 v? Okay, well, I'm going to stretch out the length of v, right, so it's the resulting vector would be 1.5 times the length of just v itself, and then with that negative, it's just going to turn the vector around. It's going to point in the opposite direction. Okay, so you can see minus 3/2 v, right, that's minus v there, and then I'm going to take another minus 1/2 of v. All right, now, what if I multiply a vector v by 0, right, the 0 scalar here, so 0v? Well, this is going to give us what we call the zero vector, which you can think of as just as a point. Okay, now I said at the very beginning of the video that vectors are quantities with both direction and magnitude. Well, there is one exception to that rule, and this is the zero vector, right? Now, the zero vector, okay, by definition, it has magnitude 0 and no specified direction. Okay, there's not a well-defined direction here that I can attach to the zero vector. Also notice here with the notation, okay, this 0 on the left, this is the zero scalar, right? So this is the 0 that you're very familiar with, right? The 0 on the number line, right? So if I multiply a vector v by the zero scalar, this results in a vector, right? And it's this vector that has magnitude 0 with no specified direction. And so you see I indicate that with the arrow. All right, well, that's a good place to stop. It just lays down a good foundation, and we'll pick up with more of this in the next couple videos. Thanks so much.